integration with complex variables is quite interesting, and maybe perhaps some stuff that you'll find that's quite powerful or unexpected. Okay, but first of all, so at first sight, it's not really that much different from real integration. So right here, if you're integrating from a to b of g of t, or g is a complex number, but the thing is right here, the kind of functions that they're looking at, they're going from the real numbers to complex numbers, okay? And so that's what that's all about. But, and that's just, this is pretty straightforward. Just integrate the real part, dt, plus the I times the imaginary part. Okay, so that's just the basic one right there. That's not too bad. That's pretty intuitive. And if you understand integration from calculus, then it's not much different. Where it gets different is what happens in reality with complex numbers is with real numbers, you're integrating along the number line, right? You're just integrating maybe an interval on the number line from a to b. But with complex numbers, what you're doing is you're integrating along a path. Okay, and so the interval is written like this. Instead of writing a lower limit and upper limit, you're writing a path. So gamma could be like a path that goes like that. And we've already parameterized. We've already done some parameterizations. And the beginning point's there, ending point's there. And then gamma of t between a and b. And so this is the definition right here. This is really important to have that memorized and learn that really well. So the integral on the path is the integral of f of z. It's the integral from a to b of f of gamma of t, gamma prime of t. Okay, so that's the definition. Let's do a few examples, just to show you what that is. So let's see, first one, let's integrate, hold on. Okay, so find integral of, I guess I should use the notation that we've been using, gamma z squared dz. So our first function is just going to be z squared. And then we'll say that gamma is the line segment from 1 to 4 plus I. I just kind of randomly chose a couple of complex numbers there. So first of all, we have to parameterize the line segment from 1 to 4 plus I. So that's when you're generally doing something like this, that could be the first step to doing it. The gamma of t. So we're going to put it in t. And then traditionally, if it's a line segment, I taught you guys that you can make your parameter go from 0 to 1. And then, do you guys remember, we wanted to go from here to here. Do you remember how to set the gamma of t up? Anybody remember?
1 minus t z1.
Yes, 1 minus t times the beginning point plus t times the ending point. Okay, so when t is 0, again, this is going to go away, and you're just going to get 1 minus. You're just going to get 1. Okay, and when t is 1, this goes away, and you just get 4 plus I. And we'll simplify that a little bit. So this is 1 minus t plus 4t plus ti. Okay, so that's 1 plus 3t, because those combine to give you 3t plus ti. Okay, so there's the parameterization right there. And now we're ready to plug it into the integral. The limits of integration are going to be these, the limits on the t, on the parameter, 0 to 1. This z is going to get replaced with all that. And then you're going to multiply by gamma prime of t, which is 3t plus I. No, it's not, it's 3. Okay, so the derivative of this with respect to t is just 3, and the derivative of that is I, so 3 plus I. So you're going to multiply by 3 plus I, and then dt. Okay, this turns out to be kind of nasty though at this point. Like I'm not wishing I should have chosen something easier. Because this is why it's 1 plus 3 c squared. Oh man, this is nasty. Plus 2 times the plus this squared, which is going to be minus t squared. And then you still have to multiply by 3 plus I. Oh, ouch. Ouch. But you guys kind of get the picture. I can continue, I guess. Ooh. I can just integrate. Let's just integrate. So the integral of this is 1 plus 3t to the third, right? Over 3. No, over 9. So what's going to happen when you take the derivative? A 3 comes down, and this goes to a 2, which you'll have there, right there. And then a 3 will come out. Okay, so that'll reduce the 9 away. Okay, and then the integral of this part is, I should expand that out. So that's 2t plus 3t squared times I. Okay, so that's going to be plus t squared. And then this one's going to be plus t cubed. And they're each going to be multiplied by I. And then this one is minus t cubed over 3. Okay, and the whole thing is multiplied by 3 plus I. And that's integrating from 0 to 1. Okay, so put a 1 in first. And that's going to give you 1 plus 3, that's 4. 4 to the third, whoa, 64 over 9. And then putting a 1 in here, you get I. Putting 1 in there, you get another I. And then putting 1 in there, you get 1 minus a third. Okay, and then subtract and put the lower limit in, put the 0 in. And that's going to be minus 1/9. Yeah. Okay, so 3 plus 5 times, let's see, combining all these, let's see, 64 9 minus 3 9 plus, no, minus 1/9. That's going to be 69. Oh my goodness. Wow. Okay, so we have to just multiply those together to get the final answer. But anyways, we're just going to leave it right there, okay? So that's how you would do an integral like that. Let me do one more example, okay? Oh, I'll do another example in a minute. So once again, this is the formula right here. Now, if we go back to this example right here, there are other ways that we can parameterize the line segment from 1 to 4 plus I. There's lots of different ways that you can do this parameterization. It doesn't have to go from 0 to 1. You can have a parameterization that doesn't even go 0 to 1. It could be 0 to 2 or -5 to 0 or something like that, you know. You could, there's infinitely many ways, literally infinitely many ways that you can parameterize this line segment from 1 to 4 plus I. But what it's saying right here is that it doesn't matter. It doesn't matter how you parameterize the line segment. This proposition right here. So here you have one parameterization, which is sigma of t, and another parameterization, gamma of t. And those are going to be the same. They're going to both give you the same results. So as long as you just come up with a parameterization, then you're good. And maybe some parameterization might be easier to work with than another one. Okay, so let me give you another example of integrating. Okay, let's find this integral here. And this time I'm going to integrate on the circle centered at I of radius 2. And I'm going to integrate dz over g minus I. And you can put a little plus there. So what this is the circle with center I and radius 2. Okay, so it looks like here's I right here. And so you go up 2 above it, 2 below, 2 to the right, 2 to the left. And it is the circle right here, and that's negative I. What we're saying with the positive orientation, that means that you're going to start here and go around this way. Because it does make a difference. It does make a difference which way you go along the same path. Okay, along the path. So you're going to start here and you go around once. And one way that you can parameterize that is like this. You can say you start with the center. Okay, so if you have the center, and then plus the radius, which is 2, e to the it. And then let t go from 0 to 2 pi. That's a parameterization. Okay, it's this radius right there. So if you have a center, so in general, this looks like z0 plus r e to the it. And then this will give you the full circle because the angle 0 is right here. This is where t equals 0. This is where t equals pi over 2. This is t equals pi, 3 pi over 2, and then back to 2 pi. So 0 and 2 pi are the same. And this is what we would call a simple closed curve. And I talked about that before. So it's That means that it doesn't cross over itself anywhere, and the beginning and ending points are the same. Okay, so that's a good parameterization for this one. So the integral, okay, what are the limits going to be of integration if we're using this parameterization?
0 to 2 pi.
Exactly, 0 to 2 pi. Okay, and also what we're going to need is we're going to need gamma prime of t. That's 2I e to the it. So taking the derivative with respect to t. If that's 0, this is just 2I e to the it. So the dz gets replaced by this gamma prime of t, which is 2I e to the it times dt. Okay, and then the denominator of those z's get replaced with this. So here we have I plus 2 e to the it minus I. Okay, so this z gets replaced with that. And then this is nice because the well, first of all, these i's are going to cancel, right? And so you're going to end up with 2I e to the it over 2 e to the it. And then the 2's cancel, and so does the e to the it's. So you just end up with the integral from 0 to 2 pi of I dt. And this is going to be 2 pi I. Okay. So that was another example of an integral. 2 pi I. Okay, so once again, the way that this works is it doesn't matter what parameterization you use, it would give all the answers. Okay, the next definition is the length. The length of a curve is defined to be the modulus of gamma prime of t dt. So let's go back to the previous problem. And we'll do this, we'll say find the length of this circle. Now, what do you think the length is, by the way? It's a circle, the radius is 2.
4.
What's the length of, what's that? You know it's going to be 2 pi r, right? Is the circumference of a circle? So it should be 4 pi. We should have, and the radius is 2, right? So it should give us 4 pi, right? So, but the length is defined to be a to b of the modulus of gamma prime of t. Okay, so in this case, what are the limits of integration again? They're from here, 0 to 2 pi. And then you take the modulus of this right here. So I'm just taking, here's gamma prime. I'm going to put that in right there. Like that. Okay, what is, so modulus of I is 1, right? What's the modulus of, do you guys remember what the modulus of e to the it is? What's e to the it? It's cosine t plus I sine t, right? And the modulus is the square root of the real part plus the imaginary part. Okay, what's cosine squared plus sine squared?
1.
Yeah, that's just 1. So the modulus of that is, the modulus of that part's just 1. So this is, modulus of I is also 1. So the modulus of all this is just 2. So the answer is 2 times the length of the integral, which is 2 pi. So it's 2 times 2 pi, which is going to be 4 pi. Okay. Or perhaps I could go do more steps. I skipped a bunch of steps right here, right? So maybe that, I don't know, if you hadn't seen integrals for a while, then that could be confusing. But anyways, the antiderivative is 2t, right? And then I'm going from 2 to 2 pi. If I put the 2 pi in for t, I get 2 pi. And then if I subtract and put 0 in, I get 0. So that's going to be 4 pi. Oops, not 3. Okay, so the length of that curve is 4 pi, which is what we expected, right? Which is exactly what we expected. Okay, now we have a few other properties. But let me do another example here. Some of these integrals can get pretty nasty, and this isn't one that's going to be even worse than the other one. So, in fact, we're going to find it. It's going to look impossible, and we'll use the exponential function. So just the exponential function. I mean, how hard can that? That doesn't seem like that's going to be too bad. And then, unless that gamma is the part of the parabola, y equals x squared, from where the origin to where x equals 2. So that's going to be 2 plus 4i. Okay, so when x is 2, then y is 4, so 2 plus 4i. So from 0 to 2 plus 4i. Okay, so gamma can be parameterized like this. If you have a relationship like this, y equals some function in x, then you can parameterize it by letting x be t, and then letting the y be whatever that function is. Okay, so here's our x. Basically, here x is t, y is t squared. If x is t and y is t squared, then y is x squared, right? So you can so if you have a relationship like this, then you can just write the parameterization like that. And then when x is 0, it's giving you the origin. When x is 2, it's giving you this point. So you can just have t go from 0 to 2. Okay, and that's the parameterization. Okay, and then gamma prime is 1 plus 2ti. Okay, so we put it in there, put everything in. Limit integration 0 to 2. Here we're going to have the exponential of t plus t squared I. And then multiply by the derivative, which is 1 plus 2ti dt. So the dz gets replaced by this times dt. Okay, and then everywhere that you see a z gets replaced by this. That's pretty, hopefully that's pretty straightforward for you guys. Okay, so I don't know, maybe it doesn't look that bad yet, but watch this. The exponential function is, this is basically e to the t times e to the t squared I, right? That's e to the t, and then e to t squared I is now cosine t squared plus I sine of t squared. Okay, now it's looking pretty bad, right? So essentially, to do it this way, you're gonna have to integrate stuff like this: e to the t cosine squared. No, cosine, not cosine squared, cosine of t squared. Okay, because there's that times that times that, right? E to t cosine t squared. That doesn't look too fun, right? That doesn't look like it's too fun to integrate. Or maybe who knows? Maybe that'd work out. So if we go that route, we get e to the t cosine t squared, and then this times this is going to give you minus 2t e to the t sine t squared. Wait a minute, maybe that can be integrated. Then you're going to have another part, right? Oh yeah, this is just the integral of this. An antiderivative of this is this. Okay, so this is an antiderivative of all that. So if you take the derivative of this, then by the product rule, you're going to be the derivative of this, which is e to the t times that, which is this term. And then plus the derivative of, plus this one, e to the t times the derivative of this. Derivative of this is going to be negative sine t squared times 2t. I say, okay, great, so that works. And then, so let's see, what is the next term is going to be I times let's do this term first. So that's times e to, so that's e to the t sine t squared. And then this times this will be 2t e to the t cosine t squared. And antiderivative for that would be just e to the t sine t squared. Ooh. Okay, because the derivative of this part is just e to the t times that. And the derivative of this part is 2t cosine t squared. So yeah. Okay, great. So we found an antiderivative. So plug a 2 in, and you have e to the t squared cosine of 4 plus I e squared sine of 4. That's plugging in 2, and then minus, then plugging in 0. you get e to the 0. And that's 0, right? Okay, so e squared cosine 4 minus 1, that's 1, plus I, e squared sine 4. Okay, so there's that example there. There's an easier way to do this. I'll show you in a minute. Let's see, where are we at page 57? There's a few properties. And the first one is a lot of stuff from the real integration just carries over. This is one of those examples where integration is is a linear function. So what that means is if you take the integral of f plus cg, that's equal to the integral of f plus c times the integral of g. So that holds. Also, negative g here would be going backwards along the path. Okay, so if you have a path right here, let's say that's g going this way, or gamma, let's say that's gamma. The negative gamma would be where you're going the other way. Okay, so if gamma is going this way along the same path, then negative gamma is going the opposite direction. That's what it is. And so reversing the direction just introduces a negative. So that's just kind of like real calculus 2, except it's with paths. And then this property right here. So what this means right here is you've got two paths. So it'd be something like this. So let's say this path is from here to here is gamma 1, and they're there. And then you have gamma 2. If gamma 2 starts right here and goes to there, and then you could say the whole thing is gamma 1, gamma 2. So that means that you'd follow this path to the end, and then at the end, gamma 2 starts and you follow that. So that's one. So you can look at it as one big path right there. And the usefulness of this is if you're given some weird path, you can define it in two different ways. So like, for example, if you, well, let me give you an example. On the next page. I'll give you an example right here. So let's suppose that find the integral of z okay, and we'll say gamma is the following. Okay, so I'll give you a path. I'll draw the path. Okay, so we'll come out here to 1. Up here to I, and back here to -1. And it goes, so basically what I want it to be is this semicircle above here, and then come back along the real axis. Okay. So start it at 1. go on the semicircle. To -1 and the positive orientation. Then go along the real axis. Okay, back to 1. Okay. So what that thing said is that we can change it into 2 paths. So that gamma 1 be this path right here along the semicircle, and then let gamma 2 be this path along the real axis. 2, not 1. And then you can parameterize. So then your integral is going to be the integral along gamma 1 plus the integral along gamma 2. Okay, so what's the parameterization for gamma 1? This is a semicircle, right? This is a semicircle. And what's the center?
0.
0. What's the radius?
1.
Now, if we were, so what you do is you act like you're gonna parameterize the full circle, okay? And what did I say that should be? If I was going all the way around the full circle.
E to the IT.
Yes, e to the IT. Good. But then on here, you cut it off at pi, like that. Just like that. And so, and then gamma 1 prime of t will be I e to the IT. Okay, so that has the first one's going to be 0 to pi of the z gets replaced with this. The dz gets replaced with this dt. Okay, so we got that. That's the first part. Now, I guess we can solve that some more. So that's I e to the 2it, right? And integrating that, you get that, right? From 0 to pi. So we get e to the 2I pi over 2 minus e to the 0 over 2. Whoa, this is unexpected. So that's going to be, whoa, I didn't expect that to happen. Really? Oh yeah, so that's going to be, that's 0, okay? But now let's check out what this one is here. We still have to add the other one to it. Okay, so gamma 2. So gamma 2, okay. So this is a line segment from -1 to 1. So you can parameterize it with 1 minus t times the first point plus t times the second point, and then let t go from 0 to 1. So that's going to be 1 or -1. And then negative t times -1 is plus t, I mean, and plus another t. So that's going to be 2t minus 1. and gamma 2 prime of t is going to be 2. Okay, so this one becomes going to go from 0 to 1 of z, which is 2t minus 1, times, then the dz gets replaced with gamma prime of t, gets replaced with 2 dt. Okay, so this is 4t minus 2 dt, and when you integrate that one, this is 2t squared minus 2t. 0 to 1. You put a 1 in, you get 2 minus 2. Subtract and put 0 in, you get that. So that's also 0. Whoa. It's all 0. Whoa. Wow. I'll show you an easier way to do this in a minute. But that was a lot of work, right? There's an easier way. Okay, so continuing along. Oh, one more thing I want to point out on page 57 is this part D. So I just showed this part right here, where if you got two different paths, then you can split up into the sum of the over the paths. Okay, part D. This is known also as the ML inequality. So if you have an integral over a path gamma, then that integral in modulus, or the magnitude of that integral, is going to be less than or equal to the maximum value of the function on the at all points on that path. Okay, so this would be all points along this path and the modulus of f. Okay, that would be the m part, the maximum, times the length, and that would be the L part, the length of the curve. Okay, so that's the ML inequality, and that's an important inequality. I think it will come up later. We'll refer back to this. I'm not sure if it's needed for this section though. We'll see. Okay, so and then page 58, we get into antiderivatives. And so just like with regular calculus, antiderivatives are important for complex variables, but it's kind of it's a more interesting connection, okay? So it talks about primitives. If f is an antiderivative, then also known as the primitive of f, okay? So and that's basically this. It's the same as before. If you have if a function f prime of z equals little f of z, so capital F is an antiderivative of little f. Okay, that's where you take the derivative of capital F and you get little f. And you have the fundamental theorem of calculus. So but there's a bunch of conditions that you have to have satisfied. Okay, so it's saying that if f is continuous and you have an antiderivative capital F, okay, if you get an antiderivative, then the integral from along the path is equal to the antiderivative evaluated at the end of the path minus the antiderivative evaluated at the beginning of the path. Okay, so this is really just like what you've seen in calculus. Very, very familiar with what you've seen in calculus. Okay. And let me show you how this works. Okay, so like I said back here, this problem right here, I said, oh, there's an easier way to do it. I'll show you in a minute. Okay, so here, we know that an antiderivative of the exponential function is itself, okay? Because we know that the derivative of the exponential function is just the exponential function, right? So that means along this path, and also we know that the exponential e to the z or exponential of z is an entire function, so it's holomorphic everywhere. So it has antiderivative everywhere. Which is important to realize here. And we know that the beginning point is the origin, that's 0. And we know the ending point is 2 plus 4i, right? So that means that this integral is going to be, the antiderivative is also exp of z from 0 to 2 plus 4i. Okay, so we know that this is going to be exponential function of 2 plus 4i minus the exponential function of 0, which is, this is going to be e to the 2 times cosine 4 plus I sine 4 minus, and this is 1, which is exactly what we have over here, see? But with a lot less work. They get the same answer, but with a lot less work. And we didn't have to like go through this kind of stuff. Okay, also, this function right here, here, we know an antiderivative for this is z squared over 2, right? Antiderivative for z is z squared over 2. And the beginning point and the end point are 1, so it's like 1 to 1. And everybody knows that's just going to be 0, right? So this problem, we could have done it much faster. We didn't have to like parameterize all this curve, parameterize all that, and then take the integral there, add them together. And we get 0 at the end. But if you just go, okay, well, this is z squared over 2 and 1 to 1. The beginning and ending point is the same, so that's just going to be 0. Or, I mean, if you want to plug this in, that's 1/2, and then minus, plug that in, that's minus 1/2, so 0 again. But I would point out, so this seems quite powerful, but let me point out that it doesn't always work that way. It doesn't always work. So let me show you. We'll go back to, let's go back to this example right here. Okay, here, we started right here at that point, and we went around and get to back to there. So we have the same the beginning and the end point are the same. They're both, what is that? 2 plus I, right? This is 2 plus I. Okay, and you would think, oh, that antiderivative is just going to be maybe the log of z minus I, right? And this is wrong though, and I'll tell you why it's wrong in a minute. But you'd think that, okay, this antiderivative is the log of z minus I, and you're correct. It is the log of z minus I, this antiderivative here. And then you'd think, okay, the beginning and ending points are the same, right? So it's going from 2 2 plus I, and then you're ending back up at 2 plus I. So then the integral would be 0 in that case. And if you plug in a 2 plus I in here, it's defined. Everything's fine. Okay. The problem is, but this is wrong, because we know already. I already showed you that the integral is 2 pi I, right? This is the correct integral. This is wrong. This is wrong. Okay. Wrong. This is not correct. It's not correct to do that. It's because the log, this log, is not defined here or anywhere back along here. Okay, and so the problem is that the path, this right here is the problem. That's the problem, that this path crosses where the logarithm is not defined. Okay, if the path didn't cross that, then this would be the perfectly legitimate way to do it. This would be great, you can do that. But because this path crosses right there, crosses where this logarithm is not defined, not differentiable, then this one doesn't work. Okay, so that's sort of like we can go back here and look at we go back to here. So the fundamental theorem of calculus for the fine print. Okay, and the fine print is that f has to be an antiderivative of f on the entire path. It has to work on the entire path. And since it doesn't, then blah, no. Okay, another way to think of it is, another way to look at it. So if you have a function that's holomorphic, so that's looking at it in terms of, so what I just showed you is looking at it in terms of the antiderivative. Okay, but if you look at it in terms of the original function, this function right here, it's not defined right here at I, and then the path encloses that. That's another way to look at it. Okay, that if the function is, if your original function is, it's homomorphic almost everywhere except at some point inside that's enclosed by this path, then it's not going. Then doing this is not going to work, or it might not work, or probably not going to work. Okay, so let's see. Continuing on. A corollary to this is, and I sort of demonstrated that with the previous problems. A corollary is this right here. And the keyword is closed. So a closed path is where the starting and the ending point are the same. So it could go all over the place and then come back to there. Okay, and that's that. So like if we had a closed path like that, and we had, let's say, the integral of, let's say this is gamma, okay? And let's say that we're saying, oh, let's take the path over, let's take the integral over gamma of z to the 4th cosine of z to the 7th exp of z minus 1 dz. Okay, what's the integral of that going to be?
0.
Yeah, that's going to be 0. Because we know that this has an antiderivative, but calculating the antiderivative is going to be kind of painful though, right? In fact, maybe impossible in closed form, but we know that it has an antiderivative. So the integral is going to be 0. And we know that the antiderivative is defined in, let's say, some region enclosed right there. So the thing is, so it's interesting. We know that this has an antiderivative, right? And then this, and then when this curve right here, how do you parameterize something like that? It's just some 4-year-old boy drew, you know? This looks like something that, you know, some child drew. But you can still take the integral over it of this function, and it's going to be 0. Okay, so that's another, that's a corollary to that. And it also kind of, you know, if it's kind of, they say it's a test for existence of antiderivatives. I guess you can use it that way. If what that means is if this is not 0, then it doesn't have an antiderivative on here. That's what that means. If it is 0, then it still might not have a antiderivative, but it could have an antiderivative. Who knows? You have to do something else. Okay. Okay, this actually, I think, is a, let me see. Okay, so continuing on. Okay, so 4.3, we're getting into Koshi's theorem. And they have this idea of that they call G homotopic with curves. So it's like comparing 2 different curves. And the example is this curve right here. So, or the example is, one example is these 2 curves right here. So you have this circle in the inside, and then you have this rectangle out here. Dang it, that didn't go very well. And then these 2 are G homotopic. Okay, because you can continuously deform the circle into the square or vice versa. And Koshi's theorem is basically saying that if f is a nice function, it's holomorphic in G. So G would be like some region containing both curves, completely containing both curves. Okay, so G is a region that completely contains both curves, and they can be continuously deformed from one to the other. Then the integrals over their paths are going to be the same. Now, the way that I like to look at it is this. So let's suppose we have the integral of f over gamma 1 versus the integral of f over gamma 2. Okay. So I'm going to draw gamma 1 to be something like this. And then gamma 2, I'm going to draw it to be something like this. And both of these, we'll give them the positive orientation. Okay, and then G is some region that contains both of them. G is everything inside. It contains everything inside. Okay, and this works. You need, for this to work, you need F to be holomorphic. And it's a region enclosing gamma 1 and gamma 2. And it's also what you call simply connected. Okay. So what simply connected means is it's connected, means everything's all connected together. And it's not like Swiss cheese. It doesn't have holes in it where it's not connected. You guys know what Swiss cheese is, right? It has holes in it. So you can't have holes in the region. So simply connected means that the complement of G is also connected. Okay, because if you tried to cut a hole out, then the complement would not be, this part over here would not be connected with the complement part here. Okay, so these integrals are going to be the same, and let me try to justify why that would be the case. If you maybe cut a little piece out of both, and then you come through like that, and you form a new curve. So like if you start here, go around there, all the way to there, and then you go in, and you go around this one, and then you go back out. Okay, so maybe that's L1, that's L2. Then, so gamma 2 followed by L1, followed by backtracking gamma 1, followed by L2. Okay, that curve, so gamma 2, which maybe is right here, goes all the way around to there, followed by going this way, followed by backtracking this, that's minus gamma 1, followed by that way. This one is a closed curve. Okay, so the integral of F on that one, if we call that sigma, then the integral of F on sigma is going to be 0 because it's closed, and F is holomorphic in this region. So this is a previous theorem we had. I think it was Koshi's. Wait, it's a previous theorem. It's the corollary of 413. So this is 0. Now, this is not what I'm trying to describe here. This is not really actually gamma 2, and this is not actually gamma 1, because you're missing a teeny piece here. But in the limit, as you move this towards this, as these get closer and closer, so you can take a limit and move these closer and closer together, and move those closer and closer together, and L1 and L2 becomes closer and closer together. Then these guys cancel each other off because they're just going the opposite direction. And then gamma 1 and gamma 2, it forces gamma 1, the integrals on gamma 1 and gamma 2 to be the same. Okay, forces those to be the same. Okay, so what that means, okay, what this means right here, which is this Koshi's theorem. Let me give you an idea what that means. If we go back to this example right here. So if we go back to this example, we know that this integral is 2 pi I, right? And that's going through with that one. Okay, so just remember that because we don't have space to do that here. So let me go back. So the integral, so if we had like, so previously we said that if you have the circle of center is I, radius 2 of dz over z minus I, that integral is 2 pi I, okay? Okay, so there's c plus I2. Okay, now, if we, from a new curve that goes like this, that's like a flower curve, ooh. Okay, and we call that gamma 2. Then the integral over gamma 2 is also going to be 2 pi I. Dang, I left the I off there. That's also going to be 2 pi I. And if we take a larger radius, like if we take a circle with a larger radius, say radius 3, that's also going to be 2 pi I. Or whatever. And also, and you can kind of see that back here when we were doing this example. Because if you look at, if you try to follow where the 2, what happens to the 2? Okay, there's a 2 right there. When we put it in here, a 2 appeared in the denominator. So if this had been a 3, then that would be a 3, but there'd also 3 appear right there, and then they would cancel, right? They would cancel, and you'd end up with 2 pi I. Even if you had like a million, then you'd have a million here, but you'd also get a million right there, and they would cancel, and you'd end up with 2 pi I still. So no matter how big you were, no matter how big of a circle it is, it's still going to be 2 pi I. The integral is still going to be 2 pi I. Okay, this looks like a good place